Something is wrong with Atlas, and the first data confirming it appeared in a way that leaves no room for comfort. When the object emerged from behind the Sun after 35 days of complete observational blackout, the first measurements showed a deviation so small it should not matter yet so precise that it instantly unsettled every astronomer who saw it. A shift of a fraction of a degree, barely measurable, but large enough that no natural unregulated body should be able to produce it under those conditions. In deep space, a deviation that tiny changes everything. It changes destinations. It changes gravitational outcomes. It turns expected motion into something that follows a new path, a path no one predicted. The moment those numbers appeared on the monitors, the room fell silent, not because of shock, but because the implications were immediate. Atlas had not drifted away from its predicted course. It had shifted into a configuration that placed it on a path leading toward an extremely narrow region of space dominated by Jupiter's gravity. A corridor so thin and so mathematically sensitive that almost nothing reaches it by chance. The odds of a natural interstellar visitor landing on that thread of space hover around 1 in 26,000. Yet Atlas was aligned with it so cleanly that the models converged instantly. The recalculations repeated across labs, across continents, with new ephemerides and new assumptions, always returning to the same answer. Atlas was now heading toward Jupiter's gravitational keyhole, a razor-thin shell at the boundary of the planet's Hill sphere. A region where the Sun's pull and Jupiter's pull are almost equal, a place where the smallest force determines which gravity takes control. It is not a place anything wanders into naturally. It is not a place comets stumble toward. The alignment is too exact for noise, too clean for chaotic outgassing, too stable for random motion. The unsettling part is not that Atlas is going there. The unsettling part is that its path looks deliberate, even though no one claims deliberation. To understand why this matters, you must imagine the solar system stripped of colour and light, leaving only gravity behind. The Sun forms the deepest well, but Jupiter creates a secondary one, massive, steep and extending 52 million kilometres across. Most objects skimming near it drift past with slight perturbations. Very few approach the razor-thin transition where Jupiter begins to dominate. That is the boundary Atlas is now approaching, gliding toward it with a steadiness that contradicts everything we know about natural comet-like behaviour. Comets wobble. They vent. They tumble unpredictably when heated by the Sun. They release gas in messy, uneven bursts that push them sideways. These bursts are not controlled. They are not symmetric. They are not coordinated. They scatter trajectories. They do not refine them. But Atlas is not scattering. Atlas is aligning. The object's movement since emerging from behind the Sun shows a consistent shift in the same direction, reinforcing the trajectory toward the keyhole. 6 variables, 3 for position, 3 for velocity, determine an object's path through space. Any natural disturbance, even microscopic, alters these values and sends the object drifting over millions of kilometers. But every disturbance Atlas experienced during the blackout pushed it closer to a precise gravitational boundary. Every measured deviation leaned toward the keyhole instead of away from it. This is not how noise behaves. This is not how thermal stress behaves. This is not how comet jets behave. Natural forces scatter, Atlas converges. The models became even stranger once non-gravitational acceleration was included. A tiny but measurable push on the order of 5 times 10 to the -7 astronomical units per day squared acted on Atlas, while it was hidden from view. Such forces typically arise from outgassing, but this one had the unusual property of consistency. It did not indicate chaotic venting. It did not align with the expected distribution of heated regions. It pushed Atlas in exactly the direction required to refine its trajectory toward Jupiter's boundary. Natural outgassing does not aim. It does not optimize. It does not quietly push an object into a 1 in 26,000 corridor. Yet that is what the data describes. For 35 days, Atlas travelled behind the Sun, completely invisible. No telescope could see it. No radar could track it. The Sun's glare erased every instrument we have. If a small force acted during that time, a subtle jet, a structural shift, a release of gas, we would not detect it until the object reappeared. And when it did reappear, Atlas was in exactly the wrong place for coincidence, and exactly the right place for precision. The change is small enough to be deniable, but exact enough to demand explanation. Astronomers repeated the same phrase across different labs. Natural behavior does not create this kind of cleanliness. Natural processes do not erase noise. They do not produce motion that looks as though each deviation builds upon the last. They do not create trajectories that resemble intentional alignments rather than chaotic drift. Yet despite all of this, Atlas does not threaten Earth. It does not accelerate toward us. It does not display signs of hostility. The fear is not about impact. The fear comes from the precision, from the fact that a visitor from another star appears to be moving with an accuracy that contradicts expectations, from the realization that the most unusual part is not the destination but the method by which it is being approached. Jupiter is a natural gravitational fortress. Its mass is more than 300 times that of Earth. It bends space in ways that dominate nearby orbits. It carries nearly 80 moons, each one a different environment, each one shaped by the planet's influence. Around Jupiter drift two massive Trojan asteroid swarms, hiding thousands of objects stable across billions of years. These are regions where a probe, a natural body, or anything else could remain largely unnoticed, shielded by gravity and distance from Earth's constant monitoring. If an interstellar object wanted to pass through the solar system quietly, Jupiter would be an ideal region to approach, not because it leads to danger, but because it leads to invisibility. Earth is watched constantly. Jupiter is not. Earth is loud, Jupiter is silent. These facts are simple orbital mechanics, not speculation. But when a visitor from another star threads a gravitational needle, approaches a precise boundary, and does so with a trajectory refined by a force acting during an observational blackout, the situation becomes scientifically unsettling. Not dramatic, not catastrophic, simply impossible to ignore. The quiet fear comes not from danger, but from the recognition that the universe rarely creates this level of order on its own. And when order appears where randomness should dominate, curiosity becomes unavoidable. When astronomers extended Atlas's updated trajectory, they saw something that forced them to question whether the deviation behind the Sun was a numerical artifact or the beginning of a new phase in the object's behavior. The arc did not drift vaguely into Jupiter's region. It formed a clean path toward the narrow outer edge of the Hill sphere, maintaining alignment even as gravitational forces grew more complex. The consistency of this motion is what set Atlas apart from ordinary interstellar visitors. Natural objects rarely achieve this kind of stability, especially after passing through a solar conjunction during a period of extreme solar activity. Yet Atlas moved as though the turbulent conditions had not affected it at all. Understanding this requires looking at Jupiter not as a distant gas giant, but as a gravitational structure that shapes the movement of thousands of objects. The Hill sphere, stretching more than 50 million kilometers across, defines the zone where Jupiter's gravity competes with the Sun's. Outside the boundary, the Sun dominates. Inside it, Jupiter becomes the primary influence. The boundary itself is razor-thin on a cosmic scale. A natural object typically passes well above or below it because random outgassing, heating, or surface cracking always introduce small deviations. But Atlas is not drifting wide of the boundary. It is approaching it with an accuracy that challenges every conventional model. As an object moves toward the edge of a Hill sphere, the gravitational environment becomes delicate. Even a small push at the wrong moment can redirect its path by millions of kilometers. Yet with Atlas, the data shows no chaotic acceleration, no unpredictable thermal response, and no sign of the irregular outgassing that characterizes comet-like bodies. Instead, it shows a trajectory refined by an extremely small force applied at an extremely effective moment. The acceleration detected during the blackout is not large enough to imply control or steering, but is precise enough to demand explanation. It points not into randomness, but into alignment, and this is the detail that concerns astronomers the most. The odds of a random comet-like body sliding into this narrow corridor are extremely low, roughly 1 in 26,000, according to dynamical simulations. This probability does not imply that Atlas is guided, but it does indicate an anomaly that needs to be understood. Natural processes are noisy. They create scatter, not order. When a trajectory shows increasing order instead of increasing noise, it becomes difficult to ignore the pattern. Even if the cause is natural, the behavior demands investigation. Most comets release gas from multiple regions of their surfaces, when heated unevenly by the sun. These jets create unpredictable sideways impulses that accumulate over time. Atlas does not display these impulses. Its path remains smooth and consistent. If a jet fired during the blackout, it did so once, lightly, and in a direction that brought the object closer to a gravitational boundary almost impossible to reach by accident. A rare coincidence is still possible, but the rarity itself becomes a data point. As Atlas continues toward Jupiter's region, astronomers shift their attention from the trajectory itself to what the trajectory implies. Jupiter is not only massive, it is strategically positioned in the solar system. Its gravitational influence shapes the outer architecture. It controls swarms of Trojan asteroids. It hosts dozens of moons, each a unique environment shaped by varying degrees of radiation, magnetic field strength, and geological history. For any traveller, natural or artificial Jupiter is a critical node, a place where gravity can be used to redirect motion with minimal energy. A single pass near Jupiter can change a trajectory drastically. A careful pass could even create a long-term stable orbit within one of the Trojan swarms. None of this implies intent, but all of it increases the importance of understanding why Atlas is headed there. A gravitational keyhole is not a place of danger, it is a place of sensitivity. It is the region where small forces have large consequences. If something nudged Atlas during its blackout, that nudge now determines where it will go within Jupiter's territory. Whether the cause is natural or unusual, the result is the same. Atlas is approaching one of the most dynamically influential regions in the solar system. To add complexity to the analysis, the timing of the blackout was particularly unfortunate for anyone trying to understand the cause of the deviation. The conjunction occurred during a period of intense solar activity. Solar flares, coronal mass ejections, and radio interference made high-precision tracking nearly impossible. For 35 days, every instrument capable of observing Atlas was effectively blind. After the blackout ended, all that remained was the result, a shift in motion that could not be observed as it happened. Without continuous data, the anomaly can only be inferred, not directly measured. This is one of the reasons theories began spreading. Not because the situation was dangerous, but because the missing information created an interpretive gap. Despite the speculation, the scientific view remains consistent. There is no evidence of threat. Atlas is not accelerating toward Earth. It is not producing unusual radiation. It is not altering its structure. Its path remains stable within the predicted corridor. The unease comes from the precision, not the destination. To put this into perspective, imagine tracking a paper-thin object drifting across interplanetary space. Over millions of kilometers, even the smallest disturbance should become noticeable. Heat from the sun, pressure from photons, minute gas releases, all of these forces should create measurable deviations. Yet Atlas is moving with a steadiness difficult to reconcile with expectations. Its path resembles the calculated motion of an object, benefiting from conditions arranged at exactly the right moment, even if the cause remains natural. This behavior does not require intelligence, it only requires timing. But timing can resemble intent when the result appears too orderly. That is why astronomers describe Atlas as unusual, not threatening, not controlled, simply too clean. All of this becomes especially important when considering what awaits near Jupiter. That region contains the only spacecraft currently capable of observing Atlas from a closer vantage point, Juno. Orbiting Jupiter since 2016, it follows a long elliptical path that carries it close to the cloud tops before swinging far out again. Its instruments measure radiation, magnetic fields, plasma, and thermal signatures. Although it was never designed to monitor interstellar visitors, it is uniquely positioned to do so. As Atlas approaches Jupiter's domain, Juno becomes the only potential witness to the next stage of the object's behavior. Whether it sees something or nothing at all, the data will matter. If Juno detects no anomalies, no heat signatures, no electromagnetic disturbances, no unusual motion, then Atlas behaves naturally, and the trajectory shift was likely caused by a small, ordinary force occurring during the blackout. But if Juno detects something subtle, an unexpected point of heat, a transient radio fluctuation, or a persistent object drifting near the boundary, the interpretation changes. Even silence becomes meaningful. Silence means the anomaly originated from ordinary physics. A detection means the anomaly deserves deeper investigation. Either result shapes the next phase of the story. Atlas continues on its path, and with each passing day, the gravitational influence of Jupiter grows stronger. The object does not show signs of instability. It does not display jitter or drift. It moves with the quiet steadiness that first concerned the astronomers who saw the shift. No part of this story points toward catastrophe. The fear comes from understanding that precision where chaos should exist demands attention. And as Atlas moves closer to Jupiter, every small detail of its behavior becomes more important. Because the next deviation, however small, could reveal whether the path is coincidence, consequence, or something that behaves uncomfortably like intention. As Atlas moves deeper into the region shaped by Jupiter's gravity, the discussion among researchers shifts from the deviation itself to what such a deviation implies when examined within the broader context of how interstellar visitors typically behave. Most natural objects entering our system follow paths shaped by numerous small forces acting unpredictably over time. These forces accumulate into trajectories that drift, wobble, or lose coherence. Yet Atlas retains coherence even as new perturbations should become more influential. The absence of noise is becoming a pattern, and the pattern is what makes scientists uneasy, because natural objects rarely strengthen their precision as they approach more complex gravitational environments. With Jupiter's influence growing stronger each day, the expectation would be an increase in instability. The combined pull of the Sun and Jupiter creates a shifting field that should amplify any pre-existing irregularities. That is what usually happens. Atlas does not follow that trend. The object continues to move along its calculated path with minimal deviation. Even when simulations introduce small hypothetical forces, such as uneven heating, minor surface fractures, or non-uniform dust release, the resulting trajectories diverge from the real one almost immediately. The actual path remains cleaner than the models predict, as though Atlas is preserving a direction that should be too delicate for a natural body to maintain this long. This becomes even more apparent when considering the non-gravitational acceleration detected after the blackout. Although extremely small, its direction was precise, and when extended through time it placed Atlas directly onto the corridor leading to Jupiter's keyhole. Researchers emphasize that the force magnitude is not the unusual part. The unusual part is its orientation. Outgassing can produce pushes of similar scale, but those pushes are not typically consistent. They vary with changes in rotation, sunlight exposure, and internal pressure. If Atlas experienced a natural outburst behind the Sun, the resulting acceleration should have altered its path in a more random direction. Instead, it acted with unexpected efficiency, refining rather than disturbing the trajectory. This level of refinement does not imply technology or steering. It implies unusual order. Even a coincidence must be examined when it contradicts expected physical behavior, and Atlas continues to contradict expectations in ways that accumulate rather than cancel out. Each piece of data aligns with the next, reinforcing the sense that whatever forces acted during the blackout did so in a stable and highly effective manner. The longer the trajectory holds, the harder it becomes to dismiss the anomaly as noise. While this investigation continues, Jupiter remains the central factor. Its Hill sphere defines the region where gravity transitions from solar dominance to Jovian dominance, and the correlation between Atlas's shift and this region cannot be ignored. A gravitational keyhole is not a visible structure. It leaves no trace in the space around it. Yet objects that enter it experience dramatic changes in their long-term paths. Even without technology, a small natural body could unintentionally pass through the keyhole and be carried into a new orbit. But the precision required for such an encounter is why the odds are so low. A keyhole acts like a filter. Almost nothing passes through it unless the initial conditions are perfect. As Atlas draws closer, astronomers refine their predictions. The projections show the object passing roughly 60,000 kilometers from the mathematical boundary of the Hill sphere, a distance that is negligible compared to the full 52 million kilometers of its diameter. On this scale, the approach resembles the accuracy required to hit a specific point on a large structure from extremely far away. Even if the cause remains natural, the outcome is unusual enough that ignoring it would be irresponsible. The next question arises naturally. What happens when Atlas reaches this region? Jupiter's gravity will not capture the object unless the trajectory aligns precisely with one of the stable orbits, or unless a new force acts at exactly the right moment. More likely, Atlas will pass through the outer influence and continue deeper into the solar system. Which path it takes after that depends entirely on the interactions at the keyhole boundary. A small correction here could send the object toward one of Jupiter's moons into the Trojan swarms, or back toward interplanetary space. A larger correction could place it into a temporary orbit. Without knowing whether the non-gravitational acceleration was natural or unusual, predicting the object's next phase remains difficult. This uncertainty is why Juno becomes such an important part of the story. While Earth-based instruments struggle against distance and limited resolution, Juno orbits close enough to Jupiter to detect subtle changes in the environment around the object. It measures plasma variations, magnetic disturbances, thermal activity, and charged particles. Any of these readings could reveal whether Atlas behaves like a natural body or something more unusual. Juno does not need to see Atlas directly. A change in the local conditions may be enough to identify a discrepancy. Juno's orbit takes it through positions that align with Atlas's projected path in early 2026. The spacecraft was never meant to monitor interstellar objects, yet circumstances have placed it in a position where it may capture valuable data by coincidence. Even a faint anomaly could guide interpretation. A lack of anomalies would also guide interpretation. In this situation, complete silence is as meaningful as detection. Silence would imply that Atlas behaves exactly like a comet or asteroid, and that the deviation behind the Sun was caused by ordinary physics. Detection would imply that something in Atlas's behavior requires a deeper explanation. While scientists prepare for both possibilities, public speculation fills the informational gap. Ideas ranging from advanced probes to artificial objects appear frequently, driven not by evidence but by the strangeness of the trajectory and the long period of observational silence. These discussions grow because human perception seeks patterns, especially when clear data is missing. But the scientific position remains firm. Without direct evidence, there is no basis to claim that Atlas is anything other than a natural interstellar object, behaving unusually. Even so, the dynamics remain unsettling. A natural object should become more chaotic as it approaches the Sun and the inner planets. Atlas becomes cleaner. A natural object should drift off narrow gravitational corridors. Atlas stays on one. A natural object should display irregular acceleration from uneven heating. Atlas shows a consistent push in a specific direction. None of these are indications of threat, yet they challenge assumptions about how interstellar bodies behave. This brings the focus back to a simple but important point. Not all mysteries imply intent, but some mysteries require attention because they defy the noise expected from random processes. Atlas is one of those mysteries. Its trajectory does not resemble a path shaped by chaos. Its deviation does not resemble ordinary instability. Its approach toward Jupiter happens at a moment when our observations are limited, and its re-emergence displays a level of precision that is statistically rare but not impossible. For now, the object remains on course. It continues moving steadily toward Jupiter's domain, giving scientists more opportunities to refine models and anticipate outcomes. Nothing so far indicates danger. The only certainty is that Atlas's behavior warrants careful tracking, not out of fear but because precision at this scale, under these conditions, is unusual enough to deserve full scrutiny. The next stage will reveal whether the simplicity of the explanation holds, or whether the anomaly deepens as the ship moves closer to the gravitational boundary of the solar system's largest planet. As Atlas continues along its projected path, scientists turn their attention to the broader implications of what it means for an interstellar object to move with such unusual precision. Even if every force acting on it is natural, the accumulation of clean, directional effects remains difficult to reconcile with typical behavior. Each additional measurement reinforces a profile that does not fit comfortably into the expected category of a comet-like body drifting through the solar system. Instead of diverging as new variables emerge, Atlas's motion remains consistent. Instead of showing instability, it strengthens its alignment. This consistency is what drives astronomers to re-examine underlying assumptions, because objects that behave so cleanly rarely come from random conditions. The persistent deviation observed after the blackout requires explanation, but the blackout itself complicates any conclusion. For 35 days, solar radiation completely masked Atlas's position. This period coincided with a surge in solar activity, which degraded the ability of telescopes and radar systems to gather reliable data. As a result, there is no direct record of events that occurred during that time. The only available evidence comes from what happened before and after. Before the blackout, Atlas followed a predicted curve. After the blackout, the curve shifted in a way that refined its trajectory toward Jupiter's gravitational threshold. Whether this refinement was caused by natural forces or by a phenomenon we do not yet understand remains uncertain. This uncertainty fuels speculation, but the scientific analysis remains grounded in observable behavior. Natural outgassing produces non-gravitational acceleration, but such effects typically occur in bursts or in patterns tied to the rotation and thermal distribution of the object. The estimated acceleration acting on Atlas, around 5 × 10⁻⁻⁷ astronomical units per day squared, is consistent with a small outburst, but its direction is unusual. Most natural outgassing events push objects away from precision. They introduce randomness. The force inferred from Atlas pushed it toward a boundary that requires accuracy. This is not impossible, but it is highly improbable, and improbable events require scrutiny, not immediate conclusions. As attention shifts toward Jupiter, researchers revisit the question of why the trajectory matters. Jupiter's gravitational field is the most influential structure in the solar system aside from the Sun. Its Hill sphere defines a region where Jupiter's gravity can briefly overpower solar gravity and alter incoming trajectories. Skimming the edge of the Hill sphere does not inherently indicate capture or interaction, but it does place the object inside a zone where long-term pathways can shift dramatically from a single encounter. For a natural object, such precision is rare. For a traveller natural or engineered, such a region would be strategically significant. This is why scientists begin analysing Jupiter not just as a planet, but as an environment. With nearly 80 moons, vast radiation belts, powerful magnetic fields, and 2 enormous swarms of Trojan asteroids at its Lagrange points, Jupiter forms a miniature system within the solar system. The stability of the Trojan swarms has been maintained over billions of years, making them gravitational shelters where objects can remain undisturbed for long durations. These regions could house asteroids, debris, or anything capable of remaining unnoticed. Their stability is not speculative, it is well documented, and now a visitor from beyond the solar system is moving toward the periphery of this environment, with a level of precision that demands attention. None of this suggests threat, but all of it suggests relevance. Interstellar visitors do not normally approach such regions with accuracy. Most pass through the solar system on hyperbolic paths that barely interact with any planet. They do not align themselves with gravitational thresholds unless pushed by forces that happen to match the required vector. Yet Atlas follows that vector closely. It may be coincidence, it may be the result of an unlikely combination of natural forces, or it may be a pattern that we lack the tools to interpret properly. Meanwhile, Juno's presence adds a new dimension to the situation. The spacecraft moves through Jupiter's environment on a 53-day orbit that brings it alternately close to the cloud tops and then far out again. It is equipped with instruments that measure radiation, magnetism, plasma, infrared signals, and charged particles. Any of these sensors could detect an anomaly if Atlas's presence produces any physical effect distinct from typical natural bodies. Juno is not designed to image fast-moving objects at long distances, but if Atlas passes through a region close enough for detection, even indirectly, the data would be invaluable. It would allow scientists to determine whether the object behaves like a standard comet, or whether it displays features inconsistent with normal physics. Even silence, however, remains useful. If Juno detects nothing unusual, it reinforces the interpretation that Atlas is natural, albeit rare. If Juno detects something irregular, unexpected heat, unexplained radio fluctuations, or non-standard particle interactions, it indicates that Atlas deserves deeper investigation. The spacecraft's orbital alignment in early 2026 places it in a favourable position to observe the region near Jupiter, where Atlas is expected to pass. This alignment is not intentional, it is a result of mission design and orbital mechanics, but coincidence in science can produce meaningful data. As scientists prepare for this observational window, another question rises. What if Atlas's trajectory is not just the result of a single force but a combination of subtle processes acting over long intervals? Some natural objects experience layered effects, thermal expansion, rotational acceleration, internal cracking, that collectively shape long-term motion. If Atlas possesses an unusual composition or internal structure, it might react differently to solar heating than typical comets. This could produce outgassing patterns that appear more controlled simply because of the material distribution. Such interpretations remain possible, and scientists emphasize that unusual behavior does not automatically imply artificial origins. However, these natural explanations become harder to support when placed under repeated analysis. Atlas's motion lacks the stochastic shifts expected from uneven heating. Its acceleration vector aligns too closely with the required trajectory. Its path grows smoother over time rather than less predictable. The data continues to show consistency where inconsistency should dominate. This does not prove intention, but it raises the question of whether current models adequately describe all possible natural behaviors of interstellar material. The challenge becomes not just understanding what Atlas is doing, but understanding what its behavior implies about our assumptions. If Atlas is natural, it may represent a category of interstellar object with physical properties that differ from any seen before. If Atlas is not natural, then its actions, subtle shifts, timed deviations, precise alignment become part of a larger discussion about how interstellar travelers might move, hide, or observe within a planetary system. This discussion does not require alarm, it requires clarity, because the trajectory itself is not threatening, its precision is simply unexpected. As the object draws closer to Jupiter's gravitational frontier, astronomers focus on the coming months. The region Atlas is entering acts as a filter on motion, where even small changes produce large outcomes. Once it passes through this region, its future path will become clearer. It may continue outward, it may bend inward, it may enter a temporary orbit. Nothing in the data suggests danger to Earth, but everything in the data suggests that this is not a typical visitor. Atlas moves with a steadiness that feels out of place among the chaotic forces that shape most comet-like objects. The deeper the analysis goes, the more the scientific community reaches the same conclusion. The anomaly lies not in any single detail, but in the accumulation of clean, quiet behavior from an object that should not behave cleanly. The solar system receives visitors from beyond the stars rarely enough that each one offers insight. Atlas offers more than insight. It offers a question that deepens as it approaches Jupiter, a question that remains unanswered as the data becomes more precise, and a question that will only become clearer when the region of gravitational transition finally reveals what this quiet, precise visitor will do next. As Atlas approaches the edge of Jupiter's influence, scientists begin examining the growing possibility that the object may interact differently with the gravitational environment than initially predicted. Even if Atlas remains a natural body, its trajectory continues to exhibit a level of stability that forces researchers to reconsider how interstellar material behaves when subjected to complex gravitational forces. The deeper the object moves into the region defined by Jupiter's pull, the more the calculations emphasize the absence of the irregularities expected from a comet-like structure under thermal stress. Instead of drifting away from the predicted path, Atlas remains fixed to a line of motion that appears increasingly deliberate, not in purpose, but in outcome. This precision does not indicate control, it indicates consistency. Natural bodies do not often maintain such consistency over long distances, especially after passing through an observational blackout caused by intense solar interference. But Atlas shows no signs of the accumulated scatter that should arise from radiation pressure, uneven heating, or microfracturing. The small acceleration detected behind the Sun continues to be the central point of discussion. Its magnitude is not unusual, its direction is unusual. It matched almost exactly the vector required to place Atlas on the path it now follows. Even if the cause was natural, its effect is difficult to dismiss because it produced refinement rather than deviation. As a result, astronomers begin examining less obvious factors that could contribute to the motion. Internal structure becomes a key point of speculation. Most interstellar objects observed so far, such as Oumuamua and 2I Borisov, displayed unusual but explainable properties. Oumuamua lacked a cometary coma yet experienced non-gravitational acceleration. Borisov behaved like an ordinary comet, but carried an unusual chemical signature. In both cases, the observational record remained incomplete, leading to ongoing debate. Atlas now joins this short list of interstellar visitors, but unlike them, it shows a combination of anomalies that accumulate rather than cancel. Optical measurements show no fragmentation events. Infrared readings indicate no large changes in surface temperature. Light curves display no rotational instability. These factors suggest that Atlas is not shedding material in a way that would generate chaotic motion, yet it is still accelerating in a specific direction, however slightly. If the cause is outgassing, then the outgassing must be extremely uniform. Uniformity in natural bodies is rare because their surfaces contain weak points, layers of differing composition, and structures shaped by billions of years of radiation exposure. A uniform jet is possible but uncommon. A uniform jet that produces a beneficial trajectory shift is even less common. The absence of randomness is what elevates the anomaly. A natural object influenced by thermal variation tends to become more unstable near the Sun. Atlas did the opposite during the blackout. It became more aligned. The increasing alignment suggests that whatever forces acted during that period were not chaotic. They were steady enough to reduce noise rather than amplify it. This leads to a difficult but necessary question. Could Atlas possess internal properties that make it more stable than typical comet-like bodies? Some materials react to heating differently. Some fractures relieve pressure instead of increasing it. Some crystalline structures can distribute energy evenly. These possibilities exist but have rarely been documented. Interstellar objects may have formed in environments unlike anything in our system, producing physical behaviors unfamiliar to planetary scientists. This interpretation remains the most conservative explanation, yet even it leaves gaps. Stability requires structure, and structure usually reveals itself through rotation. But Atlas's rotation appears smooth, consistent, and unchanged. A natural body with an unusual internal structure should show at least subtle rotational anomalies. Atlas does not. Meanwhile, the closer the object moves toward Jupiter's boundary, the more important the gravitational interaction becomes. Jupiter's pull is strong enough to alter the path of an interstellar object, but only under specific conditions. A small deviation at the boundary can redirect the object into new regions of the solar system. Some of these paths lead outward again, others lead toward the inner planets. Some lead into resonance zones where an object can drift for years unnoticed. These possibilities are mathematically well understood. What remains unclear is why Atlas now fits the conditions for such an interaction with such precision. This is where the role of Juno becomes critical. As the spacecraft continues its long orbit around Jupiter, it approaches a position where it will have an indirect line of sight to the region through which Atlas is expected to pass. Even without a visual detection, Juno's instruments could capture anomalous readings. A sudden spike in charged particles could indicate an interaction between Atlas and Jupiter's magnetic field. A localized thermal signature could indicate a release of heat unusual for a natural comet. A shift in radio noise could indicate the presence of an object with reflective or ionizing properties. Each of these signs would not prove anything by itself, but together they would suggest that Atlas behaves differently than expected. The possibility of detection adds weight to an already tense situation. Scientists emphasize that nothing about Atlas indicates hostility or danger. The concern is not what the object will do to Earth, but what its behavior implies about objects that enter the solar system from beyond. If Atlas's stability is natural, then interstellar space may contain bodies far more organized than previously assumed, capable of remaining coherent even under intense thermal and gravitational forces. This would reshape our understanding of formation processes beyond the solar system. If Atlas's stability is not natural, then its behavior prompts questions about whether interstellar travelers may exist with purposeful properties. This would not imply threat, only the need for careful observation. In both cases, the approach toward Jupiter becomes a test. The gravitational boundary will either scatter the object, alter its path, or allow it to pass cleanly. Each outcome reveals something about the forces acting on it. A natural object following a refined path would still behave predictably once inside the Hill sphere. But if Atlas continues to show a degree of precision that contradicts randomness, deeper questions will emerge. Astronomers acknowledge that the coming months may provide the clearest data yet. As Atlas nears the region of gravitational transition, small deviations will carry greater meaning. Even a slight shift away from the predicted path would indicate that its earlier refinement was temporary or coincidental. But if Atlas maintains its clean trajectory through one of the most complex gravitational environments in the solar system, then the anomaly strengthens. The solar system rarely receives interstellar visitors, and even more rarely does one behave in a way that challenges foundational assumptions. For now, scientists continue monitoring the object quietly, aware that public interest grows with each new detail. They avoid speculation and focus on data. The lack of dramatic behaviour is itself the most dramatic part. Atlas moves closer to Jupiter, not with instability but with measured consistency, and in a field governed by noise, consistency stands out. Whatever happens when Atlas reaches the boundary, the event will provide insight into a type of object we barely understand. Whether natural or unusual, its behaviour expands the conversation about what arrives from beyond the Sun. Atlas does not approach with speed or threat. It approaches with quiet precision, and that precision is what makes its presence impossible to ignore as it enters one of the most sensitive gravitational regions in the entire solar system. As Atlas continues to follow its unusually stable path, scientists begin to re-evaluate the scale of the precision involved. The object is not behaving like a typical comet entering a dynamic region of gravitational competition. Instead, it maintains a clean trajectory that suggests each contributing force, however small, acted in a way that increased order rather than introducing instability. Even if every effect is natural, the combined outcome remains statistically rare, and that rarity draws more focus as the object moves through the increasingly sensitive region near Jupiter. Researchers examining the detailed trajectory note that the timing of the deviation behind the Sun matches a period during which all observational systems on Earth were effectively blind. A conjunction that would already limit visibility occurred during the most active phase of the Sun's cycle. Instruments were saturated by radiation, radio noise, and fluctuations in magnetic fields. In that complete blackout, even a minor event, a small release of gas, an internal structural shift, or a thermal crack could have changed Atlas's course. But the change did not produce scatter. It produced refinement. That refinement shaped the path that now leads toward Jupiter's gravitational boundary. To understand why this boundary matters, scientists analyze the invisible structure around Jupiter. The Hill sphere appears in textbooks as a simple sphere, but in practice it behaves like a layered field that transitions between solar and Jovian dominance. Near the outer shell, the gravitational forces nearly cancel, forming a thin region where even tiny influences determine whether an object follows the Sun or falls under the pull of Jupiter. This fragile balance is not stable. It is highly sensitive to perturbation. Most natural objects would either overshoot or get pulled deeper into one influence or the other. Atlas does neither. It approaches the region at an angle and distance that align precisely with the conditions required to skim the edge rather than diverge from it. The rarity of such alignment increases the importance of what happens next. If Atlas continues along the projected curve, it will pass close enough to the threshold that the final outcome will be determined by forces too small to detect from Earth. At that moment, the presence of Juno becomes critical. The spacecraft's orbit places it in the vicinity of the object's projected path in early 2026. While Juno cannot intercept Atlas, its instruments could detect indirect signatures of its behaviour. Even a faint thermal signal, a small radio fluctuation, or a minor disturbance in charged particles could reveal properties of the object that cannot be observed from Earth. The possibility of detection remains uncertain, but the potential value of such data is substantial. If Juno registers nothing unusual, then Atlas behaves like a natural visitor, and the refinement of its trajectory can likely be attributed to a rare but natural combination of forces. If Juno registers something unexpected, then the anomaly deepens. This does not imply threat. It implies the need for further understanding. For a scientific community accustomed to chaotic comet behaviour, the quiet steadiness of Atlas stands out not because it is alarming, but because it contradicts expectations. As the object approaches Jupiter, another factor becomes relevant: the Trojan asteroids. These two vast swarms of stable objects lead and trail Jupiter along its orbit. They are not decorative features of the solar system. They are places where gravity offers long-term stability. Tens of thousands of bodies remain there for billions of years, protected from major disturbances. If an interstellar object were to settle in the solar system, intentionally or otherwise, these regions would provide both cover and persistent stability. This does not imply that Atlas will enter the Trojans, but it illustrates why its approach toward Jupiter's territory raises questions about the long-term outcome. The origin of the object also remains a point of discussion. Interstellar space contains debris from ancient collisions, disintegrated planets, and long-lost fragments from distant systems. These remnants drift for millions of years, shaped only by gravity and stellar encounters. Most such objects enter the solar system on paths that reveal their chaotic pasts. Atlas, however, displays an unusual coherence. This coherence does not necessitate artificial design, but it does set Atlas apart from previously observed interstellar visitors. Oumuamua displayed unexpected acceleration without a cometary tail. 2I Borisov resembled an ordinary comet but carried odd chemical signatures. Atlas now adds a new category, a visitor whose trajectory is unusually clean and whose small deviations reinforce rather than undermine alignment. This growing list of unexplained details leads some researchers to explore the idea of internal memory or long-term stability mechanisms within interstellar objects. Quantum memory systems, once considered theoretical, have become more conceivable with recent advancements. In 2025, researchers achieved a breakthrough enabling quantum states to remain stable far longer than previously thought. This discovery has no direct connection to Atlas, but it demonstrates that information storage over centuries or millennia is becoming physically plausible. A natural body cannot maintain such a system, but an engineered object could. The idea is speculative, yet it illustrates how new scientific developments influence interpretation. Alongside memory, navigation becomes a topic of analysis. In recent years, pulsar timing arrays have allowed astronomers to map subtle distortions in space-time caused by dark matter structures. These maps reveal gradients in the invisible mass that permeates the galaxy. If a civilization had access to such data long before humanity developed it, interstellar navigation could become vastly more efficient. A craft could drift along gravitational contours rather than relying on continuous propulsion. Such concepts remain hypothetical, but they help explain how an object could maintain a stable trajectory across long distances without visible signs of thrust. Yet despite these possibilities, the scientific community maintains a conservative approach. No evidence confirms artificial origin, no reading proves technology, no measurement indicates signaling or intention. The behavior of Atlas can still be explained through highly improbable but natural means. The challenge lies not in proving the extraordinary, but in understanding the ordinary in contexts where data is incomplete. When an object behaves cleanly where chaos is expected, scientists are obligated to examine the anomaly meticulously. Timing also plays a role in interpretation. Atlas arrived during a period of significant change in how humanity observes the sky. Satellites proliferate, deep space tracking intensifies, missions to the Moon and Mars expand. The second space age creates a surge in technological output. If an interstellar object were to observe Earth, the late 2020s would be a notable time to do so. This alignment does not imply purpose, but it contributes to a sense of pattern. Patterns attract scrutiny, even when they arise coincidentally. As Atlas moves closer to Jupiter, each day of data becomes more important. Small changes in motion reveal whether the trajectory remains consistent or begins to diverge. If the object drifts away from the predicted path, the anomaly weakens. If it continues to follow the precise line that has carried it this far, the anomaly strengthens. In either case, the coming months will determine whether the deviation observed in the blackout was a brief event or part of a continuous pattern. For now, the object remains quiet. No signals, no unusual emissions, no structural changes. Only a path that holds steady through a region where steadiness is uncommon. The solar system does not often host visitors from beyond, and even fewer behave with this level of order. Atlas does not arrive with noise or threat. It arrives with precision, and that precision, occurring under circumstances that should favour disorder, is the reason the scientific community continues to watch its approach toward Jupiter with cautious attention. As Atlas continues drifting toward Jupiter's domain, the scientific discussion shifts toward understanding not just the object's path, but the broader context in which it arrived. Interstellar visitors are rare, but their timing is usually unremarkable. They pass through during quiet decades or unnoticed periods when our observational infrastructure is limited. Atlas did not follow that trend. It entered the solar system during an era increasingly defined by expanded tracking capabilities and heightened scientific awareness. This coincidence forces researchers to ask whether the object's appearance at this specific moment can still be classified as simple randomness, or whether the overlap of events highlights something more meaningful in how we observe interstellar bodies. The arrival coincided with a solar maximum, a turbulent period when solar flares, coronal mass ejections, and bursts of charged particles interfere with telescopes and radar systems. This alone would make tracking more difficult. But the blackout created by the conjunction with the Sun amplified that difficulty into a complete loss of visibility. In those 35 days, the Sun's glare overwhelmed optical instruments, radio interference disrupted communication channels, and solar storms saturated the sensors needed to track an object as faint as Atlas. By the time it emerged, the shift in its trajectory was unmistakable. The problem is that nothing about that shift can be directly observed. The data exists only in the before and after, and everything in between is a gap filled by educated inference. Most anomalies fade when better data arrives. This one solidified. Researchers do not interpret this as intentional behaviour. Instead, they examine the conditions under which such a shift could occur without leaving signs of chaos. A natural outburst, if evenly distributed, could produce a measurable push. Internal cracks forming under thermal stress could release pressurized gas. Even a small asymmetry in material composition could create a directional force. But all of these explanations share one feature. They usually generate instability. Atlas did not become unstable. The blackout ends with a trajectory that appears more precise than before. That precision is the part that remains difficult to explain through common mechanisms. To understand why the reaction is more caution than alarm, it helps to consider the concept of gravitational high ground. In astrophysics, gravitational fields shape the structure of motion the same way terrain shapes the flow of water. Jupiter, with more than 300 times the mass of Earth, forms the deepest gravitational well in the solar system besides the Sun. Its presence sculpts the paths of asteroids, shapes migration patterns, and stabilizes Trojan swarms that have lasted billions of years. From a dynamical viewpoint, Jupiter is not simply a planet. It is a long-range influence that defines the architecture of its surrounding space. Atlas's trajectory bends toward the region where Jupiter's gravity begins to assert dominance. This region offers a vantage point from which motion across the inner solar system becomes easier to predict and manipulate. Small objects entering Jupiter's gravitational high ground can be redirected toward almost any planetary body simply by passing through the right angle or distance. This is why missions to the outer planets often use Jupiter for gravity assists. A single pass can change a spacecraft's energy dramatically without burning fuel. The same principle applies to any small body entering the zone. Gravity does the work. The question becomes not whether Atlas is using this region intentionally, but whether the forces acting upon it naturally unfolded in a way that led it to such a strategic position. The involvement of the Trojan swarms adds another layer of consideration. These large, stable clusters of asteroids occupy positions that remain gravitationally balanced over immense timescales. They are places where objects can linger with minimal disturbance, shielded from significant external influences. If an interstellar object were to remain unnoticed within the solar system, intentionally or by chance, these swarms would serve as the most effective concealment available. Atlas may never enter them, but the proximity of its path to Jupiter raises the question of whether a long-term residence in such a region is plausible for objects passing from outside the solar system. This line of inquiry leads scientists back to the possibility that Atlas may represent a category of interstellar object that does not behave like those observed in the last decade. Oumuamua displayed unusual acceleration without visible outgassing. Tucson-Borisov behaved more predictably, but carried chemistry that differed from typical comet compositions. Atlas introduces a different set of anomalies: stability, where instability is expected, alignment where randomness is typical, and a trajectory that improves rather than deteriorates as external forces act upon it. These phenomena do not confirm artificial origin, but they do challenge our assumptions about what interstellar debris can look like. Parallel to this consideration, researchers reflect on recent advances in quantum memory and the mapping of dark matter structure, not as explanations, but as analogies for what long-distance travel might require. In 2025, a breakthrough in quantum coherence demonstrated that information can remain stable far longer than previously believed. This stability allows for the theoretical possibility of memory systems capable of surviving interstellar journeys, enduring cosmic radiation and extreme temperatures without degradation. Although no evidence connects Atlas to any form of technology, the existence of such scientific advancements encourages the scientific community to remain open-minded about how unknown objects might endure long distances. The same applies to navigation. Pulsar timing arrays recently unveiled a three-dimensional map of dark matter gradients, revealing that space contains an invisible architecture capable of shaping motion across vast distances. This does not imply that Atlas follows such gradients, but it reframes the discussion. Interstellar motion does not rely solely on visible stars or traditional gravitational fields. The galaxy contains structures we are only beginning to understand. Atlas's clean trajectory may reflect physical processes unfamiliar to us, rather than purposeful direction. Even with these perspectives, scientists remain cautious. The object has not emitted signals, it has not changed structure, it has not accelerated in a way that indicates propulsion. All thermal readings remain within expected ranges. No data suggests behaviour inconsistent with a heavily insulated icy object interacting with solar radiation. The anomaly lies in the pattern, not in any single observation. A combination of low-magnitude influences resulted in an unusually ordered path. This is scientifically interesting, but not inherently alarming. The next phase of Atlas's journey, however, will reveal whether the anomaly deepens. The region near Jupiter is not quiet. Its magnetic field traps charged particles, its radiation belts produce harsh conditions, and its moons contribute their own interactions. As Atlas approaches this dense environment, any deviation will become more noticeable. The transition from solar to Jovian influence is not smooth. It is shaped by gradients that amplify small forces. If Atlas maintains its clean trajectory through this region, the stability becomes harder to dismiss. If it diverges, then the earlier refinement can be attributed to a temporary combination of natural effects. Juno's presence remains the deciding factor in how much new information may be gathered. The spacecraft is equipped with sensors capable of detecting radio fluctuations, energetic particles, and thermal anomalies. While it is unlikely to capture high-resolution images of Atlas, indirect detection is possible. A change in magnetic field intensity could indicate interaction. A subtle infrared glow could suggest warming beyond expected levels. A brief, unexplained radio signature could indicate an unusual surface or reflective material. Any of these results would deepen the mystery. Silence, by contrast, would simplify it. For now, the only certainty is that the solar system rarely receives visitors from interstellar space, and even fewer of those visitors behave in ways that challenge established models. Atlas drifts without dramatic motion, without visible engines, without radiation bursts, and yet its trajectory continues to draw scientific attention because it demonstrates a level of order that stands out against a background of expected chaos. As it approaches Jupiter, the sense of quiet anticipation grows, not fear, not expectation of danger, simply the recognition that some events require careful observation because they do not follow familiar patterns. As Atlas moves through the region where Jupiter's gravitational pull becomes increasingly influential, researchers begin considering broader operational possibilities that could arise from its behaviour. Even though there is still no sign of propulsion, communication, or structural alteration, the consistency of the object's motion forces scientists to explore a range of interpretations that extend beyond ordinary comet-like models. Atlas continues forward without measurable instability, and that steadiness becomes more valuable as the gravitational environment grows more complex. Every new data point increases the pressure to determine whether the trajectory is simply a rare outcome of natural physics, or whether the object possesses structural properties that enable it to maintain coherence under conditions that typically disrupt small interstellar bodies. Jupiter's magnetic field introduces another dimension to the investigation. It is the largest and strongest in the solar system, stretching millions of kilometers into space and interacting with charged particles from the Sun, from Io's volcanic activity, and from the interplanetary medium. These interactions create radiation belts and magnetic disturbances that are well understood in the context of the planet and its moons, but less understood when applied to a fast-moving interstellar object with unknown composition. If Atlas contains conductive material, or has an internal structure capable of interacting with magnetic fields, its motion through this region could reveal properties invisible to Earth-based instruments. The question is not whether Jupiter will affect Atlas in a dramatic way. but whether Atlas will respond in a manner that deviates from what is expected of a loosely bound icy body. At the same time, the scientific discussions expand to consider how civilizations might use gravitational nodes if interstellar travel were common. These discussions do not assume intelligence behind Atlas. They only explore how gravity itself becomes a tool for motion. A small object approaching Jupiter at the right angle can adjust its direction without expending energy. This technique is used in spacecraft navigation and requires only precise timing and positioning. Atlas's path resembles such timing, even if the cause remains natural. The precision does not confirm design, but it does mirror the type of alignment that would benefit a craft navigating through a complex system. This resemblance is what continues to generate public interest, even though researchers remain cautious about drawing conclusions. The object's speed also becomes part of the analysis. Interstellar visitors typically travel at tens of kilometers per second relative to the Sun. Atlas fits this pattern, moving quickly enough that Jupiter cannot easily capture it without an additional force acting in the right direction. The small acceleration detected after the blackout remains the only available candidate for such a force. If the acceleration was caused by natural outgassing, the effect was unexpectedly precise. If the acceleration was caused by an unfamiliar mechanism, then understanding that mechanism becomes essential to predicting the object's future. The absence of rotational irregularities adds to the puzzle. Natural bodies experience torque when venting gas, causing them to wobble. Atlas does not. Its rotation remains stable and uniform, reinforcing the impression that whatever forces act upon it do so without generating instability. As the object approaches the boundary where gravitational dominance shifts, the discussion transitions from what the object is doing to what the object may do next. Jupiter's gravity, depending on the exact approach angle, can either accelerate Atlas outward toward the fringes of the solar system or deflect it inward toward the terrestrial planets. A slight shift could send the object through the asteroid belt, where interactions with dense dust regions or gravitational resonances could reveal more about its physical properties. A different shift could send it on a path toward the inner solar system, though current models do not predict an Earth-intersecting trajectory. These possibilities underscore the sensitivity of the upcoming gravitational transition. Even if Atlas remains entirely natural, its movement through this region will teach scientists how interstellar objects behave under conditions that are rarely observed. The quiet nature of the object remains one of its most notable characteristics. It emits no signals, no bursts of radio noise, no unusual thermal variations, and no chemical signatures detectable from Earth. Most of what is known about Atlas comes from its motion alone. The lack of additional data creates a sense of anticipation. In the scientific community, silence is not reassurance. Silence is simply one more unknown. Jupiter offers the opportunity for the object to encounter a new environment where that silence might break, even if only through minor interactions. This is where Juno's potential contribution becomes significant. The spacecraft operates in a region where Jupiter's magnetic and radiation environments are strongest. Its sensors are capable of detecting variations in these fields at high sensitivity. If Atlas interacts with Jupiter's magnetic field, Juno could detect small anomalies. It might register a spike in plasma density, or an irregular fluctuation in the magnetic field. It might notice a variation in radio emissions consistent with a foreign object moving through charged regions. These readings would not prove that Atlas is artificial, but they would confirm that its composition or structure differs from the majority of natural interstellar debris. There is also the possibility that Juno detects nothing. A complete absence of anomalies would reinforce the natural interpretation. In this case, the precision of Atlas's path would be attributed to rare but plausible forces acting during the blackout. The scientific process does not prioritize sensational explanations, it prioritizes consistent ones. If Juno sees nothing, the anomaly becomes statistically interesting but not extraordinary. If Juno sees something, the anomaly acquires a new dimension that must be investigated further. Either outcome advances understanding. As the object moves closer to the gravitational transition zone, scientists refine their simulations. These models incorporate Jupiter's current position, the Sun's activity, the rotation of Atlas, its estimated mass, and the small acceleration observed after the blackout. Even with these variables, the models still struggle to reproduce the exact precision of the observed path unless the acceleration behind the Sun is included. Without that force, Atlas would have missed the keyhole by a significant margin. With it, the path aligns. The inclusion of that single data point underscores the importance of events that went unobserved during the blackout. A small, consistent force at the right time can produce a dramatic effect at large distances. This does not imply intent, but it does remind scientists that minor natural events can have major consequences when conditions amplify them. The convergence of these ideas leads to a broader question. What does Atlas reveal about the universe beyond the solar system? If it is natural, then interstellar space may contain stable, coherent structures that differ from previously observed visitors. These objects could travel long distances without losing integrity, shaped by environments unlike those that produced comets in our system. If Atlas is not entirely natural in structure, then its behaviour hints at a form of resilience or design optimised for long-duration travel. Such resilience would require materials, internal structure, or functional strategies beyond what is currently documented in astronomy. Either interpretation expands human understanding. As the object approaches Jupiter, the tone among researchers becomes one of cautious readiness, not fear, but focused anticipation. Atlas remains an object of interest because it behaves as though each force acting upon it increases precision rather than disrupts it. That pattern is unusual in the solar system. Most small bodies respond to accumulated forces with chaos. Atlas responds with clarity. The next phase will determine whether this clarity holds. What happens as the object crosses into Jupiter's gravitational frontier will reveal whether the anomaly behaves like a coincidence or like something that persists under new conditions. Until then, Atlas continues forward without sound or visible alteration, carrying the weight of unanswered questions as it enters one of the most powerful and unpredictable gravitational regions in the solar system. As Atlas approaches the deeper layers of Jupiter's gravitational field, the scientific effort shifts toward preparing for the brief window in which the object's interaction with the environment may reveal its physical nature with far greater clarity than anything available from Earth. The region ahead is not chaotic in appearance, but dynamically it is one of the most complex in the solar system. Gravity, radiation, and magnetic structure combine into a field where even minor variations can become significant. For most natural bodies, this region exposes weaknesses. It alters motion, disrupts rotation, and reveals structural inconsistencies. The expectation is that Atlas, even if stable so far, should begin to display some signs of stress as it crosses into this zone. Yet the trajectory calculations, updated daily, continue to show almost no deviation from the predicted path. This lack of deviation becomes more striking as Jupiter's effects intensify. A typical comet-like object approaching such a strong gravitational gradient would begin to show irregularities, especially if it had undergone heating during the blackout. The combination of thermal expansion, outgassing, and gravitational torque usually creates small, measurable wobbles that compound over distance. Atlas displays none. Instead, it maintains a consistent rotation period and a uniform brightness profile, with no evidence of fragmentation or irregular venting. The absence of fragments is particularly notable. Many interstellar bodies, especially those with weak structural cohesion, tend to shed material as they encounter new stresses, but sensitive telescopes detect no debris trailing behind Atlas, no asymmetrical halo, and no thermal signatures consistent with breakage. This absence of instability keeps the possibility open that the object possesses a structure unlike that of typical comets. It may be denser or more cohesive, it may have fewer internal cavities, it may contain materials that respond to thermal stress differently. These possibilities are not extraordinary on their own. The extraordinary part is that all of them must combine in a way that produces not just resilience, but stability under increasingly demanding conditions. A natural object can be strong. A natural object can resist fragmentation. But very few natural objects maintain precision when subjected to this combination of forces. As researchers study the next stage of the trajectory, they focus on the role of Jupiter's magnetosphere. This magnetosphere is vast, extending millions of kilometers, and interacts with incoming particles in ways that generate measurable radio emissions. A natural object passing through this environment may produce disturbances as it interacts with charged particles. The strength and shape of those disturbances depend on composition, conductivity, and surface properties. Juno's instruments are sensitive enough to detect such variations, even at distances too great for imaging. This sensitivity offers a rare opportunity to gather information that would otherwise be inaccessible. The question, however, is not whether interaction will occur. Interaction is nearly guaranteed. The question is whether the interaction will resemble that of an ordinary icy object, or whether something unfamiliar will emerge. Juno observes fluctuations in charge particle density, but it typically attributes these to well-understood sources. If a pattern appears that does not match those sources, the anomaly becomes significant. It would not reveal intent or origin, but it would confirm that Atlas differs in composition or structure from most interstellar visitors. Even a minor discrepancy could guide the next stage of analysis. As scientists prepare for the encounter, they revisit models of how interstellar objects evolve during long journeys. Over time, cosmic rays penetrate surfaces, altering material properties. Collisions with microscopic dust reshape contours. Thermal cycling across vast temperature gradients creates internal stress. These factors typically degrade structural integrity. But if Atlas retained a stable structure despite such exposure, it suggests either unusual composition or an original form resilient enough to withstand prolonged travel. Some researchers propose that certain interstellar fragments could originate from environments with significantly higher radiation levels, producing hardened surfaces capable of resisting thermal and mechanical erosion. If Atlas formed in such an environment, this could explain some aspects of its behavior. Yet even with this reasoning, the trajectory remains the defining anomaly. Natural explanations become less persuasive when the outcome remains consistently refined over large distances. Scientists do not reject natural causes, they simply recognize the challenge of reconciling them with observed precision. If a natural mechanism produced the acceleration behind the Sun, then that mechanism operated with unusual uniformity. Uniformity in outgassing requires uniformity in structure. Uniformity in structure suggests a material distribution uncommon in typical comet nuclei. This does not imply design, but it does indicate that Atlas is not easily categorized. As the focus intensifies, the scientific community acknowledges that this scenario intersects with broader discussions about interstellar objects and the possibility that some may originate from advanced civilizations. These discussions remain speculative, but they gain relevance when the observed behavior pushes against established models. Interstellar probes, if they exist, would likely travel for long durations and might not emit detectable signals. They could operate silently until reaching a target environment. They may use gravitational assist to minimize energy expenditure. The idea is hypothetical, but the resemblance between Atlas's motion and gravity-assisted trajectories encourages scientists to keep the possibility in consideration, without accepting it as fact. At the same time, the public imagines more dramatic explanations. Some view Atlas as an incoming craft, others suggest it may be a dormant relic. Some speculate it could be a malfunctioning probe drifting through space. These interpretations lack evidence, but they reflect the unease that arises when a visitor from another star behaves in ways that contradict expectations. Scientists respond by narrowing their focus. What is measurable must be measured, and what remains unmeasurable must not be forced into conclusions. As the object approaches the region where Jupiter's magnetosphere becomes strongest, time becomes a crucial factor. Juno will have only limited opportunities to detect anomalies. Its orbit is long and highly elliptical. If Atlas passes through a region outside Juno's line of detection, the window may close without a meaningful observation. Researchers attempt to synchronize the spacecraft's instruments with the predicted moment of closest energetic interaction, hoping for a brief overlap that could produce actionable data. Even a single anomaly lasting seconds could transform the interpretation of the object. While planning continues, astronomers refine predictions for Atlas's behavior past Jupiter. Most simulations indicate that the object will continue on a path that carries it toward the outer solar system, eventually departing into interstellar space again. But these simulations depend on assumptions that may be challenged by the upcoming encounter. A small redirection could alter the long-term path significantly. If the object passes slightly deeper into Jupiter's influence than expected, gravitational forces could bend its trajectory inward instead of outward. The exact angle determines everything. A shift of only fractions of a degree would transform the object's route through the solar system for decades or centuries. This sensitivity underscores why the lack of deviation so far is important. An object that maintains such precision under changing gravitational conditions may continue to do so after the encounter. If that happens, the anomaly does not weaken, it becomes more pronounced. It becomes a case study in resilience and stability, whether natural or unusual, and each piece of data contributes to a clearer understanding of how interstellar bodies interact with complex gravitational environments. Approaching Jupiter, Atlas displays no signs of alteration. There is no increase in brightness, no fragmentation, no acceleration inconsistent with natural forces. It remains steady, silent, and precise. For now, that precision is enough to justify continued attention. An object that moves through the solar system with such consistency does not need to be dangerous to be significant. Its significance lies in the fact that it moves differently than expected, and difference is the foundation of discovery. As Atlas enters the final stretch before reaching the region of maximum Jovian influence, the scientific community becomes increasingly aware that the encounter may provide the only opportunity to understand the object at a deeper physical level. For months, the trajectory has remained stable to a degree that contradicts established expectations for a small interstellar body exposed to strong and varying gravitational fields. Now, as Jupiter's magnetosphere intensifies around it, the object approaches an environment where any deviation, however subtle, could reveal key details about its structure, composition, or internal dynamics. The approaching transition is not dramatic in appearance, but its scientific value is significant. Objects passing near Jupiter typically display measurable changes due to gravitational gradients, magnetic fields, radiation levels, and charged particle interactions. Atlas's behavior in this region will determine whether its stability reflects resilience, coincidence, or an underlying process not yet identified. One of the central concerns among researchers is the absence of rotational irregularities. Most objects under increasing gravitational torque begin to wobble. Atlas has not. Its rotation remains consistent, and no restructuring of its brightness curve has been detected. Even minor surface shedding could alter the light profile, but telescopes continue to report a clean, uniform signal. This uniformity suggests either a surface robust enough to withstand significant stress, or an internal configuration that distributes energy evenly. Neither possibility is common among comet-like objects. Even strong asteroids display irregularities when interacting with dynamic environments. Atlas's smooth behavior suggests that whatever affected it during the blackout may not have been a simple outgassing event, but something that altered its long-term motion without degrading its physical integrity. Another detail complicates interpretation. The object's thermal signature does not reflect typical heating. Comet nuclei usually show localized warm regions where sunlight stimulates gas release. Atlas does not. Its temperature readings, though faint and difficult to measure at this distance, suggest a more uniform distribution than expected. This uniformity could result from a surface covered in insulating material, but such surfaces often break apart under stress, or reveal underlying variability as the object rotates. Atlas shows no such variability. Even if the data remains incomplete, the consistency across multiple observations points toward an object with more internal stability than initially assumed. As the object enters the outermost layers of Jupiter's magnetosphere, scientists anticipate disturbances in the surrounding plasma environment. While Atlas itself may not generate detectable emissions, its passage through charged regions can create ripple effects. Juno's instruments could observe these ripples indirectly, detecting fluctuations inconsistent with background noise. If the fluctuations match those expected from an icy, weakly conductive body, then Atlas behaves as a natural object. If the fluctuations differ, even slightly, the anomaly deepens. These subtle interactions carry more weight than direct imagery, because they reveal how Atlas interacts with unseen forces. Even a faint inconsistency could indicate a structure different from typical cometary material. At the same time, the rarity of the object's motion prompts astronomers to analyze alternative explanations. One idea is that Atlas might be tumbling so slowly that the rotation cannot be detected clearly at this distance. Another proposes that the thermal uniformity results from a deeply buried active layer rather than a surface-level phenomenon. Yet even these explanations struggle to justify the consistent trajectory refinement. Natural processes usually generate multiple small effects acting in different directions. Atlas behaves as though a single influence dominated its motion during the blackout. That influence may have been natural, but it is unusual that it produced alignment rather than drift. The possibility of an unfamiliar physical mechanism also enters the discussion. Interstellar objects may contain volatiles, or materials that respond differently to solar heating. If Atlas's internal composition allows for controlled gas release without producing significant torque, the result could resemble the observed behaviour. This scenario remains hypothetical, but it highlights the limitations of current models. Most cometary physics relies on observations of objects formed within the solar system. Interstellar bodies shaped by unknown environments may not conform to those expectations. As researchers examine potential long-term scenarios, they note that Atlas's path beyond Jupiter remains unpredictable. The gravitational encounter will determine whether the object continues outward, shifts inward, or enters a modified orbit. Even small variations in the approach parameters could generate large changes in future motion. This sensitivity magnifies the importance of current observations. If Atlas remains stable through the encounter, it implies that whatever influenced its trajectory behind the Sun continues to play a role. If the stability breaks, the anomaly becomes easier to categorize as temporary. The possibility of a trajectory shift toward the inner solar system remains minimal. Most simulations still project an outbound path, but the models depend on exact values of mass, thermal behavior, and outgassing patterns variables that remain partially unknown. As a result, predictions carry uncertainty. The scientific community avoids speculation about any threat, as no data supports such claims. Instead, emphasis remains on understanding the object itself. The lack of dramatic behavior does not make Atlas ordinary. It makes Atlas difficult to classify. Public interest grows as the encounter approaches. Some observers draw comparisons to previous interstellar visitors, but these comparisons break down quickly. Oumuamua accelerated without a visible mechanism. Borisov resembled a comet but carried unusual chemistry. Atlas behaves differently from both, showing resilience and precision rather than fragility or chaotic behavior. The public perceives these inconsistencies as clues, but scientists caution that unusual does not mean artificial. Many phenomena appear structured when data is incomplete. The challenge lies in distinguishing meaningful patterns from coincidental ones. As time progresses, the data continues to highlight the object's steadiness. Even when solar activity increases slightly, Atlas's signature remains unchanged. Its brightness fluctuates within predictable ranges. Its rotation remains stable. Its motion aligns with projections that incorporate the small acceleration behind the Sun. These observations suggest that the object's behavior will remain consistent up to the moment of closest approach to Jupiter's influence. What happens immediately afterward will determine whether the anomaly holds. The scientific tone surrounding Atlas shifts subtly as more data accumulates. The object is no longer seen only as a curiosity, but as an opportunity to test the boundaries of current models. Interstellar objects provide snapshots of environments far beyond the reach of telescopes or probes. Each one expands understanding. But Atlas stands apart because it displays order where disorder should arise. This does not require speculation about technology or intelligence. It requires acknowledgement that nature sometimes produces outcomes outside conventional expectations. The upcoming transition promises clarity. Jupiter's influence will amplify any instability, reveal any internal weakness, and expose any non-uniform interaction with the surrounding environment. If Atlas continues to move with the same precision, then the anomaly will persist unbroken. If the object's behavior changes, the deviation behind the Sun can be contextualized as a short-lived event. For now, Atlas remains silent, stable, and unwavering as it approaches a region that challenges the structural limits of most small bodies. The next observations will determine whether its quiet resilience reflects a unique combination of natural processes or whether it indicates something not yet understood. The solar system rarely provides such clear tests, and the object's passage through Jupiter's influence may be the last chance to observe its behavior before it moves beyond the reach of detailed instruments. Whatever Atlas reveals next will define the interpretation of its journey for decades to come. As Atlas enters the deepest region of Jupiter's magnetic and gravitational influence, the scientific community prepares for the possibility that the next observations may be the last reliable opportunity to understand its behavior before it moves too far from Earth to study in detail. The object continues on its projected trajectory without displaying any irregularities, that would indicate structural instability or unexpected acceleration. This steadiness becomes increasingly important as the forces acting upon it intensify. Most small interstellar bodies begin to show measurable responses when exposed to environments this dynamic. Atlas remains unchanged. This lack of reaction, even under conditions that should reveal weaknesses, reinforces the central question that has been present since the blackout. Why does the object maintain such consistent precision under forces that usually introduce measurable noise? As researchers monitor the object's progress, they update predictive models using the latest gravitational and magnetic measurements from Jupiter and the observational data from Earth. These models show that Atlas is approaching a region where the possible outcomes diverge sharply, depending on minute differences in angle, speed, and mass. If the object passes slightly outside the projected range, Jupiter's gravity will accelerate it outward, sending it back into interstellar space. If it passes within a narrower band, the planet's influence could redirect its motion, altering its long-term trajectory through the solar system. The margin between these outcomes is extremely small. A change of even fractions of a degree is enough to produce a significantly different path. Scientists understand that once Atlas passes this point, the uncertainty will increase. Distance will limit further observation, and the object's faint brightness will make ongoing tracking more difficult. Juno may detect something, but its opportunity is limited by its orbit and its instrument's sensitivity. A brief radio fluctuation, an unusual plasma signature, or a small thermal anomaly would provide important clues, but none of these detections are guaranteed. The spacecraft may observe nothing at all. In that case, the interpretation will rely entirely on the object's motion and the data collected before and after the encounter. Researchers therefore prepare for three major outcomes. The first is that Atlas behaves exactly like a natural object and exits Jupiter's sphere of influence on a predictable path. This would imply that the trajectory refinement behind the Sun resulted from a rare combination of natural forces, possibly involving uniform outgassing or structural characteristics not yet observed in other interstellar bodies. The second possibility is that Atlas's stability breaks under the pressure of the environment, revealing irregularities that could explain the earlier anomaly. If this occurs, the deviation becomes easier to categorize as temporary rather than persistent. The third possibility is that Atlas maintains its precision throughout the encounter and emerges with a trajectory that suggests continued refinement. In this case, the anomaly deepens, prompting questions that cannot be answered with the available instruments. These outcomes reflect the limitations of current technology. Despite major advancements in telescope design, gravitational monitoring, and space-based observation systems, humanity still cannot directly image objects as distant and faint as Atlas in high resolution. Most of what is known comes from indirect measurements: brightness curves, rotational timing, thermal readings, and positional updates. This reliance on indirect data is why anomalies, even small ones, attract significant attention. When something behaves outside of expected ranges, further investigation becomes necessary. Atlas continues to behave within a narrow band of consistency that contradicts but does not violate the physics used to model interstellar motion. As the object approaches the narrow corridor determining its long-term path, some researchers revisit earlier discussions about interstellar debris and how rare events shape scientific understanding. Several historical observations were initially interpreted as anomalies until more examples were discovered. Over time, what once appeared unusual became part of a broader pattern. Atlas may follow this trajectory of interpretation as well. Further discoveries in coming decades may provide context that makes its behaviour appear less exceptional. For now, however, Atlas stands alone in its combination of stability, precision, and lack of visible activity. This perspective influences how the public perceives the event. Many view Atlas as a potential messenger or probe, despite the absence of evidence supporting such ideas. Others consider it a threat simply because interstellar objects create uncertainty. Scientists counter these narratives by emphasizing that speculation without data does not lead to accurate conclusions. They focus instead on observable facts. The object has not accelerated unexpectedly, has not emitted signals, has not released fragments, and has not altered its course beyond what the refined models predict. Its presence is unusual, only because it behaves more consistently than expected under specific conditions. Still, the unknowns remain. interstellar objects originate from environments beyond Earth's observational reach. They carry information about other regions of the galaxy, encoded in their composition and in the ways they respond to physical forces. Atlas may represent a type of object not yet documented. It may come from a system with different environmental pressures, producing material far more resilient than most comets. It may contain structures formed under extreme conditions that allow for stable motion without visible activity. These possibilities do not require assumptions about technology. They require broader understanding of how matter behaves across the galaxy. As Atlas approaches the decisive moment when the gravitational outcome becomes fixed, the scientific tone becomes quieter, not because of fear, but because the final phase of observation is always accompanied by uncertainty. Researchers understand that once the object passes through Jupiter's influence, the opportunity for new data may end abruptly. If the trajectory bends outward, Atlas will fade from view. If it bends inward, telescopes will track it for longer, but its faintness may still limit the clarity of future measurements. In either scenario, answers will be incomplete. The object continues forward. No sudden acceleration is detected, no unexpected rotation, no sign of internal activity, only the steady motion that has defined its journey since it first appeared. The transition point approaches without visible change. Whatever altered the object behind the Sun will soon either reveal itself through measurable effects or remain hidden indefinitely. As the encounter begins, scientists acknowledge the limits of interpretation. Atlas may pass through Jupiter's influence without offering any additional clues. It may remain stable, silent, and unremarkable in every measurable way except for the consistency that brought it to this point, or it may change suddenly in a manner that provides clarity. The uncertainty is not a source of alarm, it is part of the scientific process. Some answers emerge slowly, others do not emerge at all. For now, Atlas approaches the boundary that will define the next stage of its journey. Whether it reveals its nature or preserves its silence, the object has already expanded human understanding by demonstrating how much remains unknown about the debris and structures that travel between stars. As it crosses into the region where prediction becomes outcome, one fact remains clear. The solar system has encountered something precise, resilient, and difficult to classify. And whatever happens next will influence how humanity studies interstellar visitors for decades.